Welcome to the DFA and NFA Visualizer, a project by Blake Marshall, Homero Arellano, and Jacob Sellers. The objective of the project was to build a tool that allows users to create DFAs and NFAs, and allows for a variety of options including saving and opening automata, displaying automata, testing membership of automata, and, in the case of DFAs, testing equivalence. We developed a tool inspired by JFlap, which was implemented using JavaScript and React. We used one library in this project, Joint.js, which facilitated the rendering of physical states and transitions onto the canvas. Finally, as for our development environment, we chose Visual Studio Code. By combining clear visualization and user-friendliness, our project aims to simplify automata-related problems and make theoretical concepts related to such machines more accessible. Our tool employs a systematic and modular approach to creating and analyzing finite automata. The modular design ensures a clear separation between visualization and core logic. Visualization and user interactions are handled in canvas.js. Logic modules manage membership and equivalence testing. This structure facilitates real-time updates to the graphical interface using React hooks, ensuring a seamless user experience and clean code organization. Finite automata are built interactively by adding states and transitions. States are represented as nodes on the canvas, with transitions drawn as labeled arrows connecting them. Taking a look at our project, we can see a number of options pertaining to construction operations. The addState function creates a new state with a unique identifier stored in a state management system and renders it on the canvas. This operation has a time complexity of O of 1. Transitions are added through the confirmTransition function, which updates the array of objects representing the automaton's transition function. Validations, if required, involve checking existing transitions, making the worst-case complexity O of n. Moving on, we can see options pertaining to testing membership. Membership testing determines if a string input is accepted by the automaton. Behind the scenes, it's determined in one of two ways. For DFA membership, the test input function simulates the DFA by traversing its states according to the input string, with a time complexity of O of n, where n is the input string length. This function reads the input character by character and follows the given DFA, using the current state's transitions based on the current character being read. This is repeated until the end of the input string and will either accept if the ending state is accepting or reject otherwise. For NFAs, the test NFA input function uses a depth-first search algorithm to explore all possible state paths for the given input. Its time complexity is O of the absolute value of Q times the absolute value of sigma, where the absolute value of Q is the number of states, and the absolute value of sigma is the alphabet size. Given an input, our algorithm takes into account the current state and the current character being read. From there, we discover all possible paths given the allowed transitions from each state, and find if there exists an accepting path. Moving on, we can see a number of options pertaining to testing DFA equivalence. Our tool implements DFA equivalence testing using the cross-product method. The check DFA equivalence function constructs a new DFA by combining the states of two input DFAs. Beginning with their start states, a new DFA is created that combines all reachable pairs of states from the two input DFAs. Such an approach was inspired by a quote-unquote lazy construction that we were taught in our course on theory of computation. We only compute states that are reachable and ignore all states that are deemed to be overhead. Next, XOR logic is applied to determine which cross-product states should be accepting based on the acceptance of states in the original DFAs. BFS, or breadth-first search, is then used to search for paths from the initial state to any accepting state in the cross-product DFA. The time complexity for these operations are O of the absolute value of Q1 times the absolute value of Q2, where the absolute value of Q1 is the number of states in machine 1, and the absolute value of Q2 is the number of states in machine 2. The following is a demonstration of our tool in action.
Alrighty, so this is the front end of our application, the DFA and NFA Visualizer. Upon entering, you could see that the first row, you could select what kind of machine you're going to build. The DFA, go ahead and select DFA. If it's NFA, you could select NFA, and we've provided a handy copy and paste epsilon symbol if you choose to make a transition on epsilon. So I'll go ahead and start by making a DFA, and as you can see, these will be your main two buttons for creating such machines. Add state will place a state onto the canvas that's draggable. We'll do another state. All right. Add transition. You can add a transition. It'll bring this pop-up menu where you will select the source state, the target state, and on what input character it will transition. So from Q0 to Q1, I'm going to do a 1. And Q1 to Q0, also a 1. And you could also move these states around. So I'm going to keep adding more transitions to build a DFA that should accept strings over the alphabet 0 and 1 with an odd number of 1s. Alrighty, so as you can see on the right side right here, you can see all your states and all your transitions. Before we could start testing an input string, it's going to say, oh, looks like we haven't defined our states or transitions or input properly. So you have to select the starting state, which is selectable through this drop-down menu. We'll make Q0 the starting state, and the accepting state will make Q1. So if we type in 1, 1, 1, 1, 0, that should not be accepted. And as you can see, it's not accepted, which is right. And it'll even show you the path that it took. All right, now let's add one more 1 to make it accepted. And this time it was accepted. All right. And let's say we want to save this machine. As you can see, it downloaded it to your downloads folder. And I'll show you guys that the same machine will be uploaded by refreshing, loading the machine. And as you can see, the same machine was updated, and you can still test it and stuff, and it'll still work properly. The NFA works the same way, and it'll also allow you to put the epsilon transition, exploring all possible paths from a given state, ensuring that we do capture the behavior of an NFA. Now let's say you want to test the DFA equivalence of two DFAs. So we can first start by uploading the first machine we want to test. And then we'll start by uploading the second machine we want to test. So these two are the exact same machines, so they should obviously be equal. Our algorithm works by constructing the cross product of the two machines, and from there running a BFS onto the states. And if we find an accepting state, that means that the machines are not identical or equivalent. The accepting states are determined by performing the XOR of the accepting states of these two. So it's both of them can't be accepting to be accepting in the new machine we built. So as you can see, the result says analysis complete. The DFAs are equivalent. Now I have another DFA here that I just uploaded, and we're gonna test it against the earlier DFA we built. So, and as you can see, the results say that the DFAs are not equivalent, and it tells you which distinguishing state it found. So on Q1, at the state Q1, it was found to be accepting, meaning that it should not have been equivalent. So you can see by the result message, it works.
In conclusion, the DFA and NFA tool developed in this project provides a powerful and user-friendly platform for visualizing and working with finite automata. By integrating features like membership testing and DFA equivalence checking using the cross-product algorithm, the tool provides a user-friendly approach for working with finite automata. The use of JavaScript, React, and Joint.js allowed us to create an interactive interface that supports real-time updates and ensures a seamless user experience. This project not only simplified the process of constructing and analyzing finite automata, but also served as a valuable learning experience. Through this project, we deepened our understanding of automata theory, strengthened our algorithm design skills, and gained practical experience with modern web development tools. The challenges we encountered enhanced our problem-solving abilities, and the insights gained throughout this process have made the project both rewarding and educational. If you'd like to try our visualizer, it's currently being hosted and available to use. If you'd like to browse our source code, our repository is public on GitHub. Thank you for watching. We hope you've enjoyed.